Hello everyone and welcome back to this next lecture in the machine simulation series, and this is the very first lecture of 2022, so wish you all a happy new year. So a little recap of what we did last time. We had arrived at these few equations in trying to build a dynamical model of the induction motor, single phase induction motor. So we had taken the equivalent circuit which we had already written. This equivalent circuit we had used in order to be able to compute the parameters of the equivalent circuit. And these same parameters we are also going to use in the dynamical model. So you might wonder why exactly we're going back and forth, but the reason is this equivalent circuit, the way we've drawn and also the way we have manipulated it, is extremely useful when you're doing steady state analysis. Right? When you want to calculate the efficiency of the motor, when you want to calculate the output power of the motor, the torque of the motor, the steady state speed, this equivalent circuit is used very often. However, you can't really use this equivalent circuit as it is if you want to build a dynamical simulation model. And that's where this particular equation comes into being. Or rather, this particular equivalent circuit comes into being. In this equivalent circuit, we had drawn a stator circuit and a rotor circuit as two separate circuits. So obviously the stator has a voltage. We had written the general case for which the rotor also has a voltage, though for our specific case of a squirrel cage motor, this rotor voltage will be 0. And the reason being that the rotor consists of bars which are short circuit. There is no voltage applied to the rotor. The stator winding consists of a stator resistance and leakage inductance and a magnetizing inductance. And the same can be said for the rotor as well. There is a rotor resistance, there is a leakage inductance, and there is a magnetizing inductance. So this is very, very general. Now, you can with these write these equations, and that's what we've done. So what we have said is that because this is a mutually linked circuit, we can have these set of equations. Now, in this lecture, we are going to do another deep examination of these equations we've written, because the reason is that we want to make this process of building a magnetic model as gradual and as step-by-step as possible, so that any newcomer can use this same method for modeling any kind of system. Right? So before I start the lecture, a little bit of brief background that if you're interested in these kind of video lectures but you would like something a little more comprehensive, I have full-length online courses which you can access on my own website, which is pythonpowerelectronics.com. So this home page, you can go over to the button Learn, and that will take you to the list of courses. So these are the courses which I have right now. The very first course is Simulating Power Electronic Circuits using Python, and in this I talk about the basics of how you can use Python and Python Power Electronics to simulate power electronic circuits. The second course is Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python and Python packages like SciPy and Signal within SciPy to design and analyze filters specifically for power engineering applications. The third course I have is Simulation of Magnetics for Power Electronics using Python, and in this I talk about how you can use Python and Python Power Electronics to model and simulate magnetic components like inductors, coupled inductors, and transformers. Control Analysis with Python for Grid Connected Converters is the next course. In this I talk about how you can use Python and Python packages like SciPy and Python Control to design and analyze controllers specifically for power electronic applications, and all control designs are taken with the case of a single phase power converter connected to a single phase grid. And the very last course I have is called Why Specialize in Power Electronics, and this is a free course targeted towards either junior undergraduates or high school students to motivate them towards choosing power electronics as their domain. And the purpose is to describe the challenges and opportunities available within power electronics to a power electronics engineer. So all these courses are available on two platforms, which are Decibel Labs and Udemy. If you click on any of these buttons, it will take you to the course link. So the link for this page is provided in the description for this video. If you're interested, do check out the description. So with this, let me get back to the lecture. So as I said, we had stopped here and we were writing these equations. So we had said that because the fundamental concept of a machine is that the stator and rotor are magnetically linked. and therefore any current flowing in the stator winding will produce a flux which not only associates with the stator but also with the rotor, and this is through the air gap. And conversely as well, any current that flows in the rotor will produce a flux which not only links the rotor but also the stator as well, again through the air gap. Right? This air gap of course is essential because without an air gap you cannot have a rotating machine. The machine needs a certain amount of space to rotate. But as long as the air gap is limited, we can still produce a reasonably strong enough flux which can pass through from one system to the other, that is from the stator to the rotor or from the rotor to the stator, without weakening too much. So we had said that any set of, let's say we had taken these particular, for example, I'll just highlight this. We had taken these few equations and we said that any two inductances, you can have any two coils, need not be a machine, could be a machine as well. If they have two inductances L1 and L2, we can write mutual inductances between them in this particular manner. So for example, if we assume that the mutual inductance between them is the same, in most cases it is the same unless you have a very, very special construction. This mutual inductance can be said to be equal to K into square root of L1 into L2, the inductances themselves, the products, where this K is the coupling factor. Typically this coupling factor takes into account the leakage of flux. So for example, the current flowing in the stator will produce a flux which links the stator and will also link the rotor. However, not all the flux produced by the stator will link the rotor. Some amount of the flux will be leaked, which will not link the rotor. This leakage is taken into account by this leakage inductance. But in the general case of any two inductances, it is taken into account using this coupling factor. So we take into account something like around 0.5 to 5% of leakage. Could be anything. You can choose 0.978, 0.97, 0.98. These are usually reasonable values for coupling factor. So it takes into account around 2 to 3% of leakage of flux. So now that we have these inductance, self-inductance and mutual inductance, we can write the flux linkage for the two windings in this particular manner. That is, the flux linkage of winding 1 is L1 into I1 plus M into I2. That is, the current flowing in the winding due to the inductance of the self-inductance of the winding plus the current flowing in the associated winding multiplied by the mutual inductance. And the same goes for the other winding as well. So with this, we had written these equations for the stator and rotor as well, because we said that if we can split this stator circuit into a leakage and a magnetizing component, and the same for the rotor as well, we can say that this mutual inductance between the stator and the rotor is equal to the square root of the product of the magnetizing inductance of the stator and the rotor. So it's LMS multiplied by LMR. Here we don't take a coupling factor because the leakage is taken into account separately. So with this, we can write the flux linkage of the stator and the flux linkage of the rotor. So now the question is, what do we do? Always remember, in any kind of modeling, any mathematical model or any simulation model is merely a collection of equations. The purpose is to collect these equations, to build an entire collection of equations and solve them. Now, it's important to understand that when you're collecting equations in such a manner, these equations themselves have to be interlinked. If they are not interlinked, then you're just solving independent equations. These don't really affect each other, and therefore each equation has to affect the whole system, right? That's very important. So now let's say, for example, these were general equations. Maybe I can just leave it as it is. So we can highlight these two. These are the equations of the motor that we have so far. So in these equations, we have these two equations. This is just a calculation, so it's not really an equation. We have these two equations and we have these two equations. We have altogether 4 equations. Now, if we take into account that we have 4 equations, right? Let's now find out of these equations which are independent variables, which are dependent variables, and which are parameters. So, quite obviously, the independent variables are the inputs, right? Let me just leave some space so that I can. right? So here, let me write the inputs. The inputs, as I've already said, are the voltage and the voltage applied to the stator and the voltage applied to the rotor. The voltage applied to the rotor can be 0, as in the case of a squirrel cage induction motor, or it can be some value if it is a slip ring induction motor. So let's say Vs and Vr are the inputs. When I say inputs, we are talking about independent variables that can change externally due to something which is not directly applicable to the machine itself, right? This is an external applied voltage. Now that we have this, let's write the parameters. The parameters are stator resistance, rotor resistance, leakage inductance of the stator, leakage inductance of the rotor, magnetizing inductance of the stator, magnetizing inductance of the rotor, right? And of course, once we have all this, we can also have the mutual inductance between the stator and the rotor. So with this, I think we've covered most of our parameters. Now let's look at our variables. The variables are what actually define our machine. These are the internal variables of the machine, and every variable will have a value at every instant of time. So with every instant of time, the value of all these variables denotes the state of the machine. That's usually how it is. Now, theoretically, the state of any system from a control perspective has a different connotation, but here in general terms, we can say that if we collect all the internal variables of any system, the values of these variables at any instant of time defines the state of that system, that is the condition of the system. So let's write the variables. The variables in this case are IS and IR. That's it. So we have these two variables. Now besides this, remember, we have also introduced this flux linkage, because remember, this flux linkage is not something that's external. It's very important when you define these three, you must define what is external, what is internal. So this is not external, this is internal. This is an internal calculation. We are saying that based on these currents, we have these flux linkages. So let me write that down. PS, maybe I'll write a capital PS, IS, that is psi of S and psi of R. These are variables. So we have two inputs. We have 7 parameters and we have 4 variables. The parameters don't really matter. We can have even 100 parameters. It can be any number as long as we can calculate them, and we can calculate all these from our equivalent circuit. We'll come to that later. For now, all you need to know is these parameters are values that can be computed just as we did for the equivalent circuit. So now that we have this, we now have to say that we have to solve these equations and determine these variables. That's the entire purpose of our machine model. That is, we need at all times to be able to collect our equations, and let's write our equations, to be able to collect our equations, to solve our equations and determine values of our variables. This has to be done incrementally in a simulation. Now, how many equations do we have? We have with us four equations. So now the question you might say is, we are okay. We have 4 variables and we have 4 equations. So it appears at first glance that we can solve this system and we can determine what are the variables. But even without actually going into the details of the machine, it would be naive to assume that this is all that it takes to have a machine model, because we have not even gone into the concept of a torque. We have not taken into account what happens in a torque. We have not calculated the torque of the machine. We have not calculated the speed of the machine. We have not brought in the mechanical system. So it does appear like a lot is missing, and a lot is indeed missing. So let's talk first about how we're going to bring those in, but we'll talk first about another gap that exists. So let's take a look at these two equations. As I said, the equations have to be interlinked. You cannot have all independent equations. The purpose of having a machine mathematical model is that these interlinked equations all affect each other, and therefore solving them together brings out the machine model where all the variables affect each other. Now let's take a look at these two equations. This equation is a KVL equation that we have applied to this loop. So we are saying that the stator voltage is equal to the drop across the stator, the drop across the inductance, the leakage inductance, and the drop across the magnetizing inductance. And the same for the rotor as well. We are saying that the rotor voltage is equal to the drop across the stator rotor resistance, the drop across the leakage inductance of the rotor, and the drop across the magnetizing inductance of the rotor. So this is a simple KVL equation. But if you take a look, there is no link between these two equations. We are applying a KVL loop we are applying the KVL law in this loop, and we are applying KVL law in this loop. They have nothing to do with each other. The question is that the case? That is not the case, because remember, this stator and this rotor are magnetically linked. You cannot simply write an independent KVL equation for this loop and an independent KVL for this loop, because these two systems are now linked. Therefore, these equations are wrong. It's very important that whenever you build any mathematical model, always stop and analyze the equations and go back and make changes as and how it's important. And one very important criterion is to make sure that when you see such a violation, that is, you see a KVL loop being applied between two systems that are actually interlinked, but you don't see an interlink in the equations themselves, you know something's wrong. And the reason why something's wrong is because we've not taken into account the mutual inductance anywhere in this equation. So how would I do that? The way I would do that is I need to rewrite this equation. The way it happens is we have taken this as the drop across this stator inductance. And it is not really the drop across the stator inductance. This is the induced EMF of the stator. So I'm going to change this and write ES. And the same goes here as well. That is, the voltage applied is equal to the drop across the rotor resistance and the induced EMF across the rotor. So this can be changed to ER. So now we have actually added two more equations. So we have said now the variables are ES and ER. Right? We now have 6 variables. So therefore, we now have a mismatch between the number of variables and the number of equations. But remember, we can always write equations for these variables themselves. Always remember, we are applying KVL in this loop, and we are applying KVL in this loop. If I want to write an equation for the induced EMF across the stator and the induced EMF across the rotor, I only need to use Faraday's law. And Faraday's law is, I need to say ES, that is the induced EMF across any magnetic circuit, is equal to the rate of change of flux linkages associated with that circuit. So the induced EMF across the stator, I guess it can be as it is. This is autocorrect. I'll just change it. The induced EMF across the stator is equal to the rate of change of flux linkages of the stator winding with respect to time. That is d psi s by dt. And the same goes for the rotor as well. The induced EMF across the rotor, so autocorrect is bothersome, induced EMF across the rotor is equal to the rate of change of flux linkages of the rotor. This is Faraday's law. Right? So we are using KVL, and we are using Faraday's law, and we're using the basic magnetic property that comes from Ampere's law and maybe Maxwell's law, right? These are our laws. So we have added 2 more equations, 6 equations, right? So you see what has happened now. We have now brought in the induced EMF, and by bringing in the induced EMF, we are now taking into account this particular magnetic coupling between the stator and the rotor. So our inputs, our variables, our equations, our inputs, our parameters are all now matching. So we now have achieved some level of equilibrium between our machine model and our mathematical model. But as I said, it's still nowhere near what we need. The reason? Because we have not brought in our mechanical component at all. We are not calculating our torque. We are not calculating our speed. So now the question is, what do we do? Here again, we need to understand is, as we build a mathematical model, one needs to understand is, are we capturing all the physical phenomena? We seem to have captured the current and the leak and the flux linkages, but we have still not brought in the mechanical component. So this essentially means that something is missing. And when something is missing, it means that these equations somehow are not complete. So therefore, in the next lecture, let's talk about how we can bring in the mechanical component of a machine into our simulation model. So with this, I'm going to end this lecture as it's already gotten pretty long. If you have any doubts, please do either message me on social media or send me an email, whichever is your preference. Otherwise, I will see you next week where we will continue with the mathematical model, simulation model. Thank you so much for watching and see you soon. Goodbye for now.